Greetings everyone, welcome back to Calc 1. It's time to hit those transcendental functions some more. Exponential and logarithmic antiderivatives, integrals involving exponential functions and logarithmic functions. All kinds of fun goodies inside of this section. Let's start with the basic rules that we've already seen before and let's build on them. We know that the antiderivative of e to the x is e to the x. And we actually saw a slight generalization of that one. If you remember, we had that the integral of e to the ax was equal to 1 over a e to the ax plus c. A little bit of a generalization on that one. But it involves using substitution, if you ever had to prove that one. This is the basic rule right here. And if you happen to use a different base, just like when doing derivatives, you end up with an extra ln of a multiple, except this time it's a divided factor, okay, instead of multiplied. But I've got the ln of a times a to the x. So an exponential function is still its own antiderivative. You just have that extra factor of the ln a since it's not base e. Let's actually do a couple of examples using these two rules here. Right here I see I have the integral of x to the 5th and 3 raised to the x to the 6th power. Now you've got to notice the x to the 6th is actually up in the exponent. That makes it a composition function. So what I want to do first is set up my substitution. I'm going to say that u is equal to x to the 6th, the inside function here. Then that means that du is going to be 6 x to the 5th dx. So to facilitate my substitution, I need a 6x to the 5th. And remember, we need to fix the integrals that don't already have what we need. So right here, I'm going to multiply by a 6, and I'm going to balance it out with a 1/6 on the outside. So I have 6x to the 5th dx that I can replace with du. And then, of course, u is going to be the x to the 6th. So then what I've got is 1 over 6, right? This is my substitution. 1 over 6 integral 3 to the u times du is now what I have. I've got everything all repackaged into the u and du boxes here. And to do this antiderivative, I'm simply going to lean on this rule right here, which is going to give me 1 over 6 times 1 over ln 3 times 3 to the u plus c. So let's finish this one up by consolidating. I've got 1 over 6 times ln 3, and I've got 3 to the x to the 6th power plus c. Next is not too dissimilar to the one I just did. It looks a lot more complicated because it has this denominator piece going on. But if you look at your exponent here of the e power, right, it also has its own denominator, which sort of begs the question of, hey, maybe this is linked to that. Sure enough, if I let my u equal just the exponent, and you see a pattern here, I'm hoping, because that's the same thing I did last time. I let my u be the entire exponent there, because my big function on the outside is the e to some power. Well, all right, so then my du, this is -5 over t squared. Don't forget that that can be also written as -5 times t to the -2. That's my u function, or my u substitution. And the derivative of this is going to be 10 t to the -3 dt. Or in other words, du could also be written as 10 over t cubed dt. And look at what I've got. I've got the over t cubed and the dt already ready to go. So I just need the 10, right? So I'll multiply by a 10, and I'll balance it out with a 1 over 10 right next to it. So then I've got everything I need to do the substitution. 10 over t cubed dt is du. And then I've got e and then to the u power. So my integral becomes 1 over 10 integral e to the u du, which is just an iteration of the basic rule. I've got 1 over 10 e to the u plus c, right? But then I can come back to my original system, in which case I have 1 over 10 times e to the negative 5 over t squared plus c. So exponential functions, you really just got to look for making sure that the inside function is not the exponent, right? Or, well, usually it is the exponent. And a lot of times I will be taking that if it's just an exponential with a bunch of other stuff stacked around it. The next basic rule that we need to talk about are the ones that end in a logarithm. Now be careful. In a little bit, we're also going to talk about integrals involving logarithms. But at this moment, these are integrals that end in logarithms. So let's look at these rules, right? They end in ln. The antiderivative of 1 over x is ln x. Well, absolute value, don't forget, because the ln can't handle necessarily the negatives that this integral can handle. Also, a generalization using substitution can be brought out, and this is the pattern you should be looking for. Anytime you see the derivative of something over the original thing that it's the derivative of, right? Anytime you see a function and then its derivative is on top of it, then that antiderivative is going to be the ln of that underneath function. Okay? So here's an example right away of that using substitution. I'll go ahead and do all the steps. But actually, if you recognize it, you don't need to necessarily go through all of the steps. If you see that pattern, you can jump straight to it. But let's go through the steps here. I notice that I have an x to the 7 and an x to the 6 here. And then right above it, I have x to the 6th and x to the 5th. Well, it's just a big red flag screaming, hey, this might very well be the derivative of this guy right here. Okay, fine. Let's double check. If I let u equal the bottom, 6x to the 7 minus 4x to the 6th, take the derivative of it, du, is going to be equal to 42x to the 6th minus 24x to the 5th dx. It's almost right. The numbers are a little bit off. But if you factor, 42 and 24 both contain a 6. Like so. So notice that's exactly the piece that I have in the numerator there. And all I'm missing is a multiplied 6. Well, we can fix that, right? We're just going to multiply by 6. And I'll balance it out with a 1 over 6 out front. Then what I've got is an integral 1 over 6 with a 1 over u du, because all of this replaces for du. That means that I have 1 over 6 times ln, the absolute value of u. But then back to my original function, I have ln, absolute value of 6x to the 7 minus 4x to the 6th. In the absolute value, mind you, that's important because the ln can't handle any of the negatives, but the original integral could. So I put the absolute value in there to make sure that this answer can reflect any possible values that come from the integral in giving me the antiderivative. Sometimes when you have an integral with a fraction, you might be tempted to say, I wonder if I can use an ln with that one because it has this fraction and I don't see anything else going on. Well, every once in a while you can, but you need to manipulate the integral first. And I don't mean just with the numbers, like balancing out those. I mean, it's almost looking like something that could be something with a logarithm, but it's missing some key vital elements. Like if I wanted this bottom to have a derivative that was equal to the top, then it would have to have an exponential up there, right? Because I have an exponential down here. Well, I can fix that. What I'm going to do is I'm going to multiply the top and the bottom by e to the x. And why e to the x, you say? Well, e to the x times e to the negative x will give me e to the 0, which is 1. But it'll also give me a 2e to the x here and a 2e to the x here, which will give me the top and bottom exponential relationship that I need. So then this is equal to the integral 2e to the x over 2e to the x minus 1 dx, like so. Now, do you notice that if I were to take the derivative of just this bottom piece, the 1 would go away, and the derivative of 2e to the x is 2e to the x. So if you were to do a substitution by letting the bottom be your u, then this would be my du right here, exactly, 2e to the x dx. So what is this going to equal out to? I'm just going to use the rule this time. I see a derivative over its original, so it's going to be equal to the ln of the absolute value of 2e to the x minus 1 plus c. I didn't have to fix it anymore after that, right? No numbers or anything like that, because that is exactly the derivative of this one. So I'm just invoking that property, okay? It's basically a shortcut past all the substitution, and which is fine, okay? If you'd rather do the substitution, just let u equal this piece in the bottom, and you'll see that this gives you your du, and it'll all come together perfectly fine. Okay, next. Here's an integral involving a logarithm. Be careful. I'm not actually going to integrate the ln this time, though. What I'm noticing is that I have an ln squared. Remember what that means? That's mathematician shorthand in trig, right? We put the exponents in between a function and its argument to show that this whole thing is actually squared. So what I've actually got is the ln 4x quantity all squared. So that means the ln of 4x is actually an inside function. So look, if I let u equal ln of 4x, it would be taking a piece of an inside function there, which is what substitution usually does. So then what would du be? Du would be 1 over 4x times 4 times dx. Right? Because the derivative of ln of something is 1 over it, and then the chain rule would pop out a 4. But notice these 4's would actually go away, and my du is actually equal to 1 over x dx. That's what du is equal to, 1 over x dx. Do I have that? I sure do. Look, I have 1 over x dx. Right? Right. So, this is what's going to happen. What I have is an integral. I've already got my substitution ready to go. 1 over x dx is ready to go. So I've already got my du. And what's left over is a u squared in the bottom, and the 7 is still there in the bottom as well. Great. I've replaced something and made it look a lot simpler. The 7 in the denominator is just in the way. I'm going to pull it out front to get it out of the way. And this is really just u to the negative 2 du. That's all it is. Great. So then from here, I'll have 1 over 7 times negative 1 u to the negative 1, because remember, you add a power, then divide by the new power, plus c. So then let's finish this up. I've got negative 1 over 7u plus c, right? Because that's what the negative exponent does. But I don't want u. I'm going to go back to what I originally had it as. That's going to be equal to negative 1 over 7 ln of 4x plus c. And there it is. So even though there was a logarithm in the integral, I didn't actually do an antiderivative of a logarithm yet. We haven't talked about those yet. We're going to a route to. So these are the basic integrals that can come up for exponentials and logarithms. What I want to show you in the next few scenes is some of the other structures that can be built around these basic ideas. Next, let's see some examples of how the exponential and logarithmic functions mix together with some of our trigonometric iterations. So notice I have e to the 5 sine 4x times cosine 4x dx. And that one should almost be screaming out at you what exactly we need to do if you've been practicing your substitution, right? Because you can tell cosine is the derivative of sine. You're going to look for any of those trigonometric pairs that have that function derivative relationship, right? It could have been tangent and secant squared, or it could have been secant and secant tangent, or any of those like that. But for this one, sine with cosine. And just like before, what we'll do is we'll let our u take the place of the exponent. So here, I'm going to let u equal 5 sine of 4x. Then du will be equal to 20 cosine 4x dx. So let's go through that, real quick. Let's make sure you're with me. The 5 was already there and followed me along. The derivative of the sine gave me the cosine of the 4x. And then, of course, it's a chain rule. So derivative of the 4x popped out. 4 times 5 is 20. All right, well, what do I have in the integral? I have cosine 4x dx. Of course, I'm missing the 20. So I'll have to fix that. I'll do times 20 and divided by 20, so that now I can substitute all of this for du. Okay, so what we have is equal to 1 over 20 integral of e to the u du. Of course, the antiderivative of e to the u is e to the u plus c. So I have my 1 over 20 e to the u, but then of course I need to convert back to my x variable. So I have 1 over 20 e to the 5 sine of 4x plus c. Right? Okay. Next, I have sort of the reverse. What if I have an exponential inside of a trig function? It's completely fine. Works exactly the same way. I'm going to do my u substitution as the inside function, which in this case I'm seeing the secant squared, but I'm noticing the exponentials both inside and outside. So then this would have to be my inside. I'll have to let u equal e to the 5x, because that's the inside function. Also, I know that e to the 5x's derivative is itself, so I need this piece out there. Let's finish that up. Du is equal to 5 e to the 5x dx. Uh-oh, I have 4 e to the 5x. And I can't use addition or subtraction. No. Instead, what I'm going to have to do is take this 4 outside, get him out of the way, And I'm going to multiply by an extra 5. So times 5 divided by 5. The times 5, it doesn't really matter where I put it. If you can imagine that I'm actually squeezing the times 5 here, whatever. The dx, the 5, and the e to the 5x, all three of those pieces get packaged up into du. 5 times e to the 5x times dx. All right, so then I've got 4/5 integral of secant squared of u du. Right, because I have secant squared and then that's u. And now I just need to know what the antiderivative of secant squared is. Well, that's one of our basic rules, right? So I've got 4/5 times tangent of u plus c. But of course, u is equal to e to the 5x. So I just substitute it back. Okay, now let's switch gears a little bit here. Here are some integrals that result in logarithms, but they have to do with our trig functions. Okay, now these top two are just some basic ones that you really need to know for a lot of other things that will come up in this calculus and the next. And then here's an example of how a logarithm can still be involved in one of these integrals and yet still not necessarily need to be integrated. Right here, I have tangent of x. But before I just say, well, what is the antiderivative of tangent x? Right? It's not one of those rules that just rolls right off. Instead, what I'm going to do is I'm going to rewrite it. I'm going to rewrite as the integral of sine x over cosine x dx. And then once you rewrite tangent as its alternate form there, you realize, oh, this is a fraction where the bottom is the original and the top is the derivative. Sure. Right here, notice the derivative of cosine is negative sine. Well, wait a minute, we've got positive sine. I can fix that though. So here's what I do. I bring out a negative and bring in a negative. Negative is positive, right? Okay. According to that rule we had last seen, remember, if I have a derivative over its original, then that's equal to the ln of the absolute value of the original. So the negative sine x, that's the g prime. That's the derivative. And then cosine x, that's the original. That's the g of x. This negative here is along for the ride. And then it's going to be ln absolute value of cosine x plus c. All I did was I invoked the rule from last scene, where if you have a derivative over its original, right? ln of the original. An alternate on this one, by the way, worth mentioning, is that since I can bring any multiplied numbers in, I could also say, or this is equal to ln of the absolute value of secant of x plus c. Okay? Both of these are valid antiderivatives of tangent. Okay? And all it is I'm just bringing the negative 1 in as a power. Cosine to the negative 1 is 1 over cosine, which is secant. But either one of those, if you take the derivative, you will end up back with tangent again. Okay? Another one like that, where I need to do a little bit of reconfiguring first, and then I can invoke my derivative over original ln antiderivative. Okay? So here's what I'm going to do to this one. I'm going to start off by multiplying something that you wouldn't think of right away. It's over 1, right? Now, unless you've seen this before, typically this isn't something you just think, oh, let me just multiply this. But watch, it just falls apart once you do this. If I multiply the top and the bottom by secant plus tangent, like that. Secant plus tangent, like that, of x. Okay? Now, once I simplify these multiplications, I'll have the integral of, I'm going to multiply this into both of these. That's going to give me secant squared plus secant tangent. Dx is still here. And notice in the bottom, I'm just going to reverse the addition. Tangent plus secant. I didn't actually change anything. I just felt like, swapping the order, just like 3 plus 2 and 2 plus 3, the same thing, right? I did that, though, so that you can see the pattern. Do you notice how they're both additions, right? Derivative of tangent is secant squared, and derivative of secant is secant times tangent, right? So that means that the derivative is the top and the original is the bottom. G prime of x over g of x. So I can invoke that antiderivative with an ln rule, which is going to give me the ln of the absolute value of secant x plus tangent x plus c. And yes, I know I reversed the addition. The addition doesn't matter which way you write it. Okay? So those are two very important antiderivatives that are much easier to work once you understand that the antiderivative ending in an ln type of rule. Now this one is an integral involving a logarithm again, and yet again, I will not actually be doing the antiderivative of the logarithm. It just happens to be part of the integral. Okay? Notice our pattern over here. Do you notice that the ln of secant has a derivative of tangent, right? Because this is antiderivative. So if I go backwards and take the derivative of this, I will get tangent back again. Well, look, ln of secant, and then here's a tangent, right? So if I let u be all of this ln right here, all of it, its derivative will involve this tangent, right? So here I go. I'm going to let u equal ln of secant of 7x, right? So then du, as we've just seen, the derivative of ln of secant is tangent of 7x. But then also I have to do the derivative of 7x, so 7, and of course dx, because I multiplied the dx over for my substitution. Okay, so I've got my derivative now, and let's look at what I've got over here. I have 4 tangent 7x dx. I need 7 tangent 7x dx. So I'll have to fix with the multiplications like we've been doing a few other times, right? I'll need to bring this 4 outside. And then I'll need to multiply by a 7, right? So times 7 goes here. And then divided by 7 will go here. All right. So 7 tangent 7x dx, that gets packaged up into du. And then all of this ln is u. So I'm left with 4/7 integral u du. Right? This is u. And then all of this is du. So then I just need to do this integral here. 4/7 times 1/2 u squared plus c. Right? Because I add a power, divide by the new power. Then this is going to be equal to 2/7. And what was u equal to? The ln, right? So 2/7 times ln of secant of 7x plus c. And then wait, what about the squared, right? So it's squared. Remember, that's shorthand. The squared in between something like a logarithm or a sine or a cosine and its argument. If the exponent is between the two, it actually means the whole thing as an object is squared, and I just don't have to write an extra set of parentheses, right? It doesn't mean that it's ln. It means it's ln secant 7x, whatever that is, and then square that whole value, right? That's what this means. So I've got that squared. So I wanted to throw in these couple of rules, mostly just in case you have this underlying curiosity of why don't we have any integrals with logarithms already inside them, and I'm actually going to be finding some antiderivatives with those logarithms. They don't come up as often, but we can do them. We do have formulas for them, as you can see the two formulas here. The proofs of these formulas are reserved for the next course of calculus because they require a more advanced method of integration that is typically reserved for the second course. But I will show you the formulas just so that you know this does exist, and also in case you happen to run into an application here and there where you might actually have to integrate a logarithm. So the antiderivative, the integral, the indefinite integral of ln of x, notice no absolute value, not needed in this case, is equal to x times ln x minus 1. Some people may also say it's x ln x minus x, and all they're doing is distributing the x there. I left it in this format because it's easier to see the symmetry with the generic logarithm one. If it's any other base logarithm other than e, then the antiderivative, the indefinite integral of log base a of x dx, is the same thing. I have x ln x minus 1, you see. But it's just divided by ln of a, which is really just a result of the change of base formula from this logarithm here. That's really all there is to it. Okay, so let's do a couple of quick examples here so that you can see that these work practically the same. It's not just ln of x here, but I do notice that my derivative is 1. So it's one of those borderline ones where I don't always feel that there's a necessity for substitution, but being that I'm trying to show you the steps, I'm going to go ahead and do it. So here we go. U is going to be equal to x minus 4, the inside function, which means du is equal to 1 dx, or just dx. Okay? Whenever you have a du equals dx, that substitution is mostly for your own benefit and clarity of structure. Okay? However, can still be done. So here I go. Dx just becomes du. X minus 4 becomes u. So I'm going to bring the negative 8 out. Integral ln of u du, which, as we've seen up here, is just going to be negative 8 times x times ln of x minus 1 plus c. Oops. Big boo-boo. What did I do wrong? I'm not in X universe right now. I'm in the U universe right now. Woo! Big boo-boo. Now I do my substitutions back into the X universe. That's going to be negative 8 times U is equal to X minus 4 times the ln of X minus 4 minus 1 plus C. Right? Okie dokie. Over here, there's no substitution necessary. It's just a different logarithm base of x. And don't forget, when it's log with no base written, it's an understood base of 10. You have that button on your calculator also. Log base 10 is useful in many STEM fields as well, just like ln is useful in a lot of physics and chemistry, and some biology as well. Log base 10 has its roots in a lot of those same fields. It has to do with pH. It can be used with the Richter scale and earthquakes and things like that. So log base 10 might be something that comes up for you as well. Now, to do this integral, I'm just going to remember that I can bring my 5 outside, and then my a is the number 10. So then what I've got here is just going to be 5x over ln 10 times ln x minus 1 plus c. And I'm just straight using the fact that the 5 was pulled out and just multiplied and brought over. And then it's pretty much the same formula as the rest of it. I'd like to finish up with a couple of quick examples of some generic applications in STEM. Just remember that a lot of the stuff we've already talked about in other lectures before this one still apply. All of the same applications are there, and the things that you'll be integrating very likely will be things that are rates or rate of change or something like a measured change in something, where you're going to want to integrate to do the opposite of the derivative, basically. There are other things like finding area and things like that, but the main point is to remember to look for something being called a rate or not, right? And then also just, keep an idea of what net and total and displacement and things like that are all going to apply to you. That being said, let's do a couple of these examples. A lake contains fish whose population grows at a rate of p prime of t. Now, of course, I'm kind of giving it away by calling it p prime of t there, okay? But remember, if it's a rate of something, right, then it's some sort of change in something. It's the measured change. So it's basically a derivative at each moment. This particular rate changes over time. It grows over time. The rate grows. That should make sense to a population. The rate at which the population is going to increase is going to keep increasing, since the population itself is growing and uses itself to grow, right? This one's kind of steep, but it's an exponential. So my population rate of growth is given by this function per month, right? So t is just measured in months, basically, is what it's saying. All right. So if the lake starts with an initial population, right, at time 0 of 15, what's the total population after 1 year? Well, don't forget a year, but we're measuring in months, right? So we're going to do an integral of the first 12 months. And don't forget that what this is sort of like the net change applications that we did recently with some of the other lectures that have just gone by. Okay, so I'm going to be using this particular formula where f of b is equal to f of a plus the integral from a to b of f prime of x dx. That's basically what I'm going to be doing. Some books call it the net change theorem. Some people just recognize it as an alternative to the fundamental theorem of calculus. Basically, I have a starting point plus adding up all of the changes in between. That's really all I'm doing. So my p of 12, in other words, after 12 months, right, is going to be equal to p of 0, which is the 15, plus, right, I'm doing p of 0 here, plus the integral from 0 to 12, because this is p of 0, here's p of 12, right, of the derivative, the rate of change. So that's 38 e to the 0.04 t dt. So then I just need to perform this definite integral and then add 15, right, and we're done. Okay, so let's do the antiderivative portion first. This isn't a fancy substitution one. This is just a number times t, but you can do a substitution if you want. Here I'll be doing 15 plus, And then I've got the antiderivative here is 38 divided by 0.04 e to the 0.04t from 0 to 12. All right. So let's see. From here, that's going to be 3,800 over 4. So then, let's see, 800 over 4 is going to be 200, right? And then the 3,000 divided by 4 is going to be 750. So then what I have here is 15 plus 950 times, and then I'm going to do e to the 0.04 times 12. So that's e to the 0.48 power minus e to the 0 power, which is just 1. All right, and so now I'm going to crunch this up here. 15, let's start with the e to the power of 0.48, right? So e to the power of 0.48 is 1.616. I'm going to subtract the 1, right? So 0.616 times 950 is 585.27 plus 15. I've got 600.27. And of course, it doesn't make sense really to talk about 0.27 of a fish. So we'll just say it's around 600 fish. All right. So in reality, you got to remember that derivatives are actually easier to measure than actual values sometimes, just depending on your measuring devices and whatnot, because that is an actual change. So you may very well have started in a real situation with a function that measures a derivative rather than an actual population. And then you may have to do some sort of net change in order to figure out different values. Okay, next I have a particle moving along a line. Okay, it has an initial velocity of 5 already, 5 feet per second, that it's moving along this line. And then as it's moving along this line, something comes behind it and pushes it even more. Okay, and this is the acceleration that is acted on the particle due to this force pushing it in the same direction that it's already moving. So the particle is moving, and then something comes along and gives it another force. And this is the acceleration that results from that. Okay, so it's still traveling in that line. And the acceleration, notice, for as long as t is greater than 0, I'm going to have nothing but positive acceleration, which means my velocity is going to do nothing but increase. And my velocity is starting at 5. The good news on this is that means my velocity will never go negative, right? I won't have to worry about separating this into all of the different cases for total distance. Remember, total distance, sometimes we had to separate it where it was positive and negative and things like that. We can already see that since acceleration is going to always be positive, my velocity is going to always increase. And it already started off as a positive velocity, so it's going to stay positive the whole time. So, what is the total distance traveled from 2 seconds to 6 seconds? Well, I'm not to total distance yet because I haven't gotten to velocity yet. I'm still at the acceleration level, right? Don't forget, acceleration is the derivative of velocity. So my velocity function, d of t, is going to be equal to the antiderivative of this, right? Okay. Maybe a better way to really think of it is that the a of t is actually just v prime of t. That's another way of thinking of it, right? And what I'm actually going to do is the antiderivative of this, right? I am going to perform this task here. That antiderivative is going to give me a plus c though, and I'm going to use my initial velocity here as an IVP, an initial value problem, so that I can figure out what my actual velocity function is. Okay, so I'll be doing this antiderivative, which means I'll be pulling the 4 out like this. And then I notice that 1 is the derivative of t plus 1. So this antiderivative must be ln, where the bottom function is my g of x, remember? And then the top is g prime. So I'm going to invoke that logarithm antiderivative. And what I have is 4 times the ln of the absolute value of t plus 1 plus c. So my velocity function must be equal to this right here. This must be my velocity function, but I've got a plus c in there. So okay, fine. This right here is telling me that v of 0 is 5, because it's the starting velocity right at the very instant that the force started. So that is my initial velocity. So what that's telling me is 4 times ln of 0 plus 1 plus c is equal to 5. That's what that is telling me. Well, of course, 0 plus 1 is 1. ln of 1 is 0. So this is just zeroed out, and this is telling me my initial value problem is actually giving me a velocity function where c is 5. Okay, so my actual v of t is 4 ln, and I'm going to put parentheses here. Let's talk about that for a second. I found my velocity function, and I'm not using the absolute values, even though that was part of my antiderivative. Well, we said the acceleration was only when t was greater than or equal to 0, right? Well, as long as t is greater than 0, or even at 0, t plus 1 is always positive. So I don't need the absolute values. The absolute value of a positive is just going to be the same positive number. So I can actually leave off the absolute values in this case, because I'm never going to run into a negative inside of my ln. The absolute values just don't make a difference here. Okay, now I've got my velocity function. Some problems will actually start here. They'll say, oh, look, here's the velocity. Total distance. Remember, total distance, you have to look out for whether the velocity is positive and negative in the different sections, so that you don't accidentally just add up displacement. Good news for us. This function is always positive, as we saw earlier, right? 5 is positive, 4 is positive. Logarithms only give out positive numbers when their insides are bigger than 1. And these will be, right here. This ln would only be negative if I could get this to be less than 1 in here. T would have to be negative, and it can't be. So this function right here is always positive. I don't have to split it up. I can simply do my total distance with one definite integral from 2 to 6 of 4 ln t plus 1 plus 5 dt. All right, well, here we go. There's an application where I have to do an antiderivative of a logarithm. First, I'm going to start out with my substitution, right? My substitution here is u equals t plus 1, so that I can make this simpler right here. All right? Then du is equal to dt. That's lovely. That means it was one of those substitutions that you didn't necessarily have to do, but it can help you see the structure. Okay. So then I'm going to have the integral of 4 ln of u plus 5 du. Right? Haven't changed anything. So then, right here, these were t values, right? These were t values. So if u is equal to t plus 1, then right here, when t is 2, u is 2 plus 1, 3. And right here, u is 6 plus 1, 7. Now, because of the way the substitution is set up, I don't have to go back to t. I can simply crank out this calculation right here. Okay, so let's do that. The antiderivative of the 4 ln u is going to be 4u times ln of u minus 1. And then antiderivative of 5 is just plus 5 times u. Okay? Now, of course, this is going to be evaluated from 3 to 7. Let me consolidate a little bit. If I distribute this 4u into this parentheses, notice I'll have a negative 4u plus 5u. That will save me some punch time. What I have is 4 times u times ln of u, and then negative 4u plus 5u is just plus u again, from 3 to 7. Okay, so now let's actually throw in the numbers and see if we can't get an approximate value here for the final answer. I'm going to have 4 times 7, which is 28, times ln of 7, plus 7, minus, throw in the 3, and I'll have 12 ln of 3, plus 3. All right. So let's see. From here, let's just go ahead and crank out the approximations, because there's other things you can do to bunch this up. Of course, I could distribute the negative, and then we could combine these with logarithm properties. In the end, it's really not going to do me any favors saving me time or anything like that. So I'm just going to punch it in as I see it here. 28 ln of 7 plus 7. All right, then I've got minus 3 and minus 12 ln of 3. So I'm getting approximately 45 here. Approximately 45.3 feet total here. All right. So all of these applications that we run into are not that much different than with all of the other different functions that we've been handling. In this section, I just needed you to see how we handle exponential and logarithmic functions and how they mix with other functions. And I hope that this helps you see that substitution as a whole is still a very powerful integrating structure.